Hey guys, another snow day. Here we go. Anyway, what we'll do today is we'll continue, at least in part, from where we left off yesterday, and we'll kind of more or less stay on schedule. We're going to get to the quiz cutoff point today, but I'm not going to have you guys take the quiz tomorrow because I want to at least be able to kind of touch base and talk with you guys tomorrow. Hey, Anders, you need to plug them in. My son's here, so he's having trouble plugging his headphones into the iPad. So anyway, so quiz will be on Monday, not tomorrow, and we will continue these notes. I'll show you the quiz cutoff point is. Tomorrow, I'll briefly kind of review some of these things, and then we'll continue on after the quiz cutoff point. But the quiz on Monday will only cover up to the quiz cutoff point that we will see here today in this video lecture. So, all right, so we left off talking about sort of fates of radiation, wrapping up kind of our conversation about radiation. Remember, you know, the allotment of energy that our planet receives is through solar radiation. Now, what ultimately happens with that radiation, it can either be absorbed, transmitted, right, or, this up a little bit, can ultimately be reflected or scattered, right? And when we talk about reflection or scattered, reflection really refers to, you know, completely bouncing off. Scattering refers to the radiation is redirected, or what we'll talk about today, in a way, diffused. So you'll see what I mean by that, right? Now, so we sort of left off here. You think of the 100% allotment of energy of solar radiation that our planet receives. Only 50% of it, right, actually ends up, right? Only 50% of it actually ends up being absorbed by our planet's surface. So that's land and water, right? Yes, Anders? Nothing. Okay. He's being a goofball. All right, and then the other 50%, 30% of it is either reflected or scattered back towards space by the atmospheric clouds and reflective surfaces. So especially reflective surfaces like snow, water, and ice or glaciers, right? So we talked a little about these like positive feedback loops and the idea that, you know, snow, water, ice, glacial ice plays a significant role in the maintenance of this number. Okay, it's good that 30% is reflected and scattered back into space because, again, this prevents ultimately too much absorption. It prevents ultimately too much absorption. So we'll get more into that in just a second, right? But this idea of the changing status of our climate has caused a loss of these reflective surfaces. Now, you increase the loss of these reflective surfaces, what do you have? You have more absorbent surfaces, like more land, more water. Consequence is more of this radiation is now being absorbed. So we'll get more back into that in just a second, right? Right. Next. Sorry. So this next graphic sort of just talks about what we just said, just to kind of give you a visual. So again, thinking about solar radiation, 100% allotment, right? What happens to it? Okay. I gotta clear 100% allotment of radiation. So 50% of it, both direct and diffuse radiation, are absorbed by land and sea. Okay, so our planet's surface, 50% of it's absorbed. Again, you know, what happens to the other 50%? 20% of radiation absorbed by the atmosphere and clouds. Okay, and then 30%, and we move this. Okay, 30% is lost back into space by straight up reflection or backscattering or scattering off of surfaces. Right? So the 30%, where does that come from? So 5% backscattered to the space by the atmosphere. That's so reflection and backscattering of solar radiation directly off of our atmosphere. Remember, our atmosphere plays a role in protecting from and certainly preventing certain amounts of radiation from reaching our surface, like that of the ozone layer, and preventing of ultraviolet radiation, some of the ultraviolet radiation from reaching our surface. 20% is reflected from clouds, so cloud coverage, that's a good thing on our planet. Cloud coverage plays a role in backscattering or reflecting 20%. Okay? And then the last, land and sea surfaces. So our planet's surfaces reflect about 5%. Okay? So 5 down here, and then again, more reflective surfaces mean more light, less reflective surfaces mean less light, okay? Or less radiation, I should say. But here's the breakdown. 5% here plus 20% here plus 5. So 5 plus 20 plus 5 is 30%. So 30% is lost back into space through reflection and scattering. Okay? So reflection and scattering, let's discuss that a little further. Okay? Reflection, this is where it bounces back at some angle at which it hits at the same intensity. So here's sort of the deal, like as radiation hits a surface, or as it hits, atmospheric gases, as it hits any reflective surfaces on our planet, as it hits clouds within our atmosphere, that which is reflected back, it hits and bounces off or bounces back at the same intensity. It doesn't affect the intensity of the energy that's carried with it. Now, I bring up a term called albedo right now. Okay? So albedo is the fraction of the radiation that will be reflected back when a surface is impacted by some form of radiation. Now, in general, Earth has about a 30% albedo overall. Right now, again, that's on average across the board. Land, water, ice, whatever, doesn't make a difference. On average, overall, our planet has about a 30% albedo. Meaning that on average, right, about 30% of solar radiation is reflected backwards, which makes sense because we just said here on this previous slide, 30% is lost to space by reflection and scattering. Okay. Now, there are different surfaces that will exhibit different albedos, and we'll kind of return to that. Now, this by comparison to what's called scattering. So scattering is diffused light. So diffused just means, like it's sort of broken apart in a way. It's weakened when solar radiation or when radiation impacts certain surfaces. It causes or affects, I should say, it affects the energy by reducing it. So these weaker rays will end up traveling in different directions. It scatters, the radiation. There's this thing called forward scattering versus back scattering. More energy is moved forward than backward. This would be considered forward scattering. The energy that's moved backwards is called back scattering, and back scattering is going to result in loss of energy off of our planet. Okay? Now, scattering and even reflection, and for that matter, will be exhibited by the presence of like specific gas molecules, dust, different surfaces on our planet that are going to cause these two sort of fates of radiation to happen. Right? So this is just sort of an image to kind of demonstrate this idea of reflection versus scattering. So on the left here would be an example of reflection. Okay, so imagine here's a molecule of gas in our air that's good at ultimately, or does not allow the transmittance of radiation. So here's this electromagnetic wave, solar radiation coming in. It directly impacts that particle. It's impacting it on some angle, and then it reflects back off at the same angle, and it possesses the same amount of energy. Okay? Whereas on the right side here, this would be a picture of scattering, where, so here's that same, you know, radiation source as it impacts, you know, that particle or that object, as opposed to it being reflected backwards or at an angle that has an equal energy, it gets diffused or scattered. You sort of get this impression that as it impacts that particle, it sort of blasts it apart, you know, in a sense. And each one of these sort of smaller forms of radiation end up, some of it is forward scattered. Okay, so this would be the energy that ends up forward scattering. This would be the energy that ends up back scattering, right? So you got it. Some of that energy gets back scattered, and that energy that gets back scattered gets lost off of our planet's surface. Okay? Yes, Sanders.
I love you.
I love you too, buddy. All right. So moving onward. Oops. I need to clear all drawings. So going with this, we talked about albedo with that of reflection, right? Albedo is a measurement of the percent reflected. Now this is a table right out of your book in chapter 15. It has albedos listed of various surfaces, objects, whatever you want to call it. Now, on this list, there's some things that I want to kind of point out, right? So, you know, clouds and things like that, you know, pretty decent albedo, you know, 25 to maybe 55%. So clouds are a pretty good reflective surface, right? But then as you sort of look down at this list, and this kind of brings me back to, okay, things like concrete, crops green, forests green, meadows green, roads, blacktop, sand, some of these things, plowed field, you know, these are all pretty low albedos. You know, we're in the 5 to maybe 30 to maybe upwards of 60%, right? Water, 8%, right? Soil, dark soil, 5 to 15%. Soil, even light or desert soils, 25 to 30%. But as you look at snow, this would include like ice as well. You know, albedos of, you know, upwards of 70, 80 to 90%. Okay. So when we kind of get into this conversation about climate change and global warming, right? The idea is that with climate change, okay, with greater amounts of solar radiation ultimately being absorbed, lesser amount of heat loss resulting due to climate change, this reduces the amount of snow and ice on our planet's surface, which then further reduces the amount of solar radiation that gets reflected off our planet's surface. Consequently, this causes greater temperature increase. All right, we'll talk a little more about that in a minute. Okay. So now, again, kind of back to absorption. And we've said this, gases are sort of selective absorbers, meaning some are good at absorbing, some are bad. For the most part, most gases within our atmosphere are pretty transparent. Okay, they're poor absorbers. They allow radiation to move pretty well freely through. Okay. Nitrogen is a poor absorber, you know, and our atmosphere is mainly nitrogen, 70% nitrogen. So nitrogen more or less allows solar radiation to move through. Oxygen and ozone are pretty good at absorbing UV radiation, so ultraviolet radiation. This accounts for such a high temperature in the stratosphere. We talked a little bit about this earlier in this unit. So oxygen and ozone are pretty good at absorbing a specific section of radiation. Water vapor is a pretty good absorber, right? As it says at the bottom, Earth's atmosphere is essentially transparent. It doesn't acquire energy, heat from the sun. Most of the solar radiation that is able to move through, that doesn't get, you know, immediately scattered back out into space. Our atmosphere is not heated by or through the radiation that moves through it. It's chiefly heated from energy that is first absorbed by our planet's surface and then re-radiated back out into the sky or atmosphere as heat. So again, think of that example we talked about yesterday, that the blacktop parking lot at the mall. Okay, that thing's getting hit with the noonday sun all day long, and ultimately, you shut the lights off. The sun goes down at night, and you can still feel that heat re-radiating back off of that surface. Right? That is happening, really all over our planet's surface to more or lesser degrees. And how is the air and our lower atmosphere heated? It's heated by that re-emittance of heat off of our planet's surface after it has been, the solar radiation light has been absorbed. Right, let's go to the next slide. Okay. So, talking about the greenhouse effect, it's a natural process. We've talked about this a little bit before. It's good. 50% of solar radiation reaches the surface and is absorbed. Okay. Most of this is re-radiated skyward at a lower temperature and longer wavelength. Okay. Now, water vapor and carbon dioxide are both pretty good absorbers of this longer wavelength energy. So, the consequence is the atmosphere heats up. So water vapor, carbon dioxide, other what are called greenhouse gases, you've heard me say that before, are good at this heat, okay, this lower temperature, longer wavelength energy that's being re-radiated off of the Earth's surface after it's been absorbed as solar radiation. These components of our atmosphere, water vapor, carbon dioxide, are good absorbers, along with other greenhouse gases like methane, at absorbing this energy and preventing it from just basically moving back out into space freely. So this is important. This is what heats up our atmosphere and makes it habitable to life. It warms our atmosphere, makes our climate, our climates accessible or livable. Okay? There's Anders sneaking in the background again. Say hi. Seriously, say hi. Oh, don't do that. That's scary. All right. So this is important. It heats our atmosphere and makes it habitable to life. Right? So much of the incoming short wavelength solar radiation penetrates the atmosphere, heats Earth's surface, like we talked about. Now, as this surface absorbs that energy, it re-emits that energy, right? Okay. Back out into this longer wavelength, lower temperature energy. Okay. So greenhouse gases absorb this outgoing long wavelength radiation and traps that heat in the lower atmosphere, ultimately causing our lower atmosphere to warm up. Right? That's the greenhouse effect in a nutshell. All right, Anders. You can say hi for real now?
Hi.
All right. Now, moving on. Having to do with the greenhouse effect versus global warming, or like we've talked about before, the term that we like to use more now is called climate change, because it's not just about warming temperatures. This is bad, right? With the greenhouse effect, Earth would be too cold and uninhabitable. So the greenhouse effect is a good thing, obviously. But here's the deal. So human activities are enhancing the natural process of the greenhouse effect. By adding CO2 and other greenhouse gases, usually through industrial uses of fossil fuels, we're changing the balance of the carbon cycle, and we're inputting more, especially the thing of most concern is CO2 into our atmosphere. We're experiencing levels of CO2 in our atmosphere that have never been seen in our planet's history. And this major change, and this input of CO2 coincides with the beginning of the Industrial Revolution and has ultimately caused major changes within our climate. Mainly, the first idea is that global warming. Yes, global average temperatures are on the increase. Okay? The consequence of that is pretty far-reaching. We've talked a lot about this. Okay? And I want to rehash one last time these idea of positive feedback loops. The interesting thing about climate change is that You know, we've talked about this. We're really at this really sort of tipping point where we have to really start to make and think about some real wholehearted changes. We're seeing, you know, consistently higher and higher global average temperatures year after year. We're seeing, you know, global average sea level rise. We're seeing all these sort of consequences that go along with that. But then we're also seeing the fact that these positive feedback loops exist. Again, when I say positive, it doesn't mean positive in a good way. It just means positive in the fact that the result of global warming or climate change actually drives global warming or climate change even further. So the example of ice, remember, ice and snow has a really high albedo, okay, than say land or water surfaces. Right? Well, as global temperatures have risen, it's led to the loss of much of the world's, and we're seeing a consistent reduction in the world's glacial ice coverage. Consequence of that is less solar radiation is being reflected back out into space. More solar radiation is being absorbed by our planet surfaces because we literally have surfaces that are not ice covered. Now we have land surfaces, rocky covered surfaces that are greater absorbers. Well, more solar radiation absorbed, more heat gets re-emitted by our planet surfaces, thus warming the lower atmosphere even more. Okay? So ice has a higher albedo than water. Ice has a higher albedo than that of land surfaces. So this then further causes a temperature increase, which further propagates or pushes climate change even faster. So it has this sort of snowball effect on what climate change is doing or happening. Okay? All right, so that's where I want to cut things off for the quiz for Monday, 4:15. So that marks the end of today's lecture. We'll get into talking a little bit about temperature measurement and data on Monday. Okay? I'm sorry, tomorrow. I will go back over and talk about some of the things from this video lecture tomorrow. But watch this video and, you know, take some notes from it, and we'll go from there tomorrow, guys. See you guys tomorrow.